So then we have to see that whether this this gradient transport assumption still holds or not, and for that we will introduce a very simplified reaction scheme where we will not consider all this linear this exponential form etc. We will just, and we will even neglect essentially the exponential form and just say that the for dependence on temperature we will just consider a very simplified reaction where this this thing is shown by, is given by the reaction, the production and consumption rate of the species I is given by minus rho times B times psi I. Okay. So this linear reaction scheme where we have just totally ignored the exponential part, we will see that how we can show that this is does not hold. And then of course if you go back to the Ti, that is the scalar time scale, which is I double prime square averaged by the scalar dissipation rate. Okay, and if we now set this production equal to dissipation equal to this covariance of velocity fluctuation and scalar fluctuations, we get of course we get that one. Plus some additional contributions due to the since your chemical time scale now becomes important. Okay. So here we have assumed, basically the assumption is that balance of production, dissipation and reaction terms in the transport or evolution equation of okay. So then this gives you get the dt, but you get additional contributions from this okay. So and actually in this case you will see that your T by tau I with B tilde varies like this. Okay. So B is essentially the comes from this your reaction term, okay, and this is 2.0. So this is B tilde equal to 0. So I will see that that when does the gradient transport assumption hold? The gradient transport assumption will hold when this is equal to 0 and this is equal to 1, okay, or rather this is equal to 2 this thing, okay. So so this will hold only then. But you see that the problem is that when B tilde becomes large, this thing becomes very small, okay. So then when these two are small, okay, that is when these two are very small, then this this equation, when this is small then this becomes big, and when this becomes small then this becomes big. So these two becoming simultaneously becoming equal to 1, this case does not really happen. So as a result of this, the gradient transport assumption fails in most cases when you try to apply this for the reactive scalar, okay. So basically, and you see that as what happens is that as B tilde increases, this T by tau I goes to 0, okay. So as this goes to 0, of course then this goes to become small, and this the smaller the quantity, the far and far is being deviated, this assumption is gets deviated from the basic gradient transport assumption. And physically this results from the change of the scalar fluctuations that is brought about by the chemical reactions. So chemical reactions, actually what it does is that chemical reactions consume the scalar, okay. So when they consume the scalar, the local scalar fluctuation reduces, because the scalar can go to, the value can go to 0 or it can reduce. Okay, it can be produced as well, but it can go to, it can change from the actual scalar value that was in place. So that chemical reaction introduces scalar fluctuations, and as a result of that, this this gradient transport, there is a result of the scalar fluctuations are not independent of the reactions. The reactions contribute to the scalar fluctuations, they can reduce it, and as a result of that, the gradient transport assumption for non-reactive scalars may not hold for the reactive scalars. So this was the so here of course this will be Favre average. So this was the thing. So gradient transport assumption is a problematic thing for combustion, and you will see that sometimes in combustion we assume that gradient transport or counter gradient transport, as the situation may be. Okay. So next what we will do is that next we will go into some practical modeling approaches that is used for turbulent combustion, and that one uses to solve large situations as it using so these approaches are typically implemented in commercial codes like Fluent, etc., ANSYS Fluent. So we will just go over this to see that how by introducing simple assumptions we can have a reasonably okay, rather crude closure for the source, for the mean source terms. So that we will proceed in the following. Okay. So for that, so to that closure, of course we will go into better closures. We will go into more refined models like the transported PDF model and the conditional moment closure models, the G equation model and the flame net models in the later non-premix flame and premix flame classes. So, but to give you just a flavor of how the commercial codes work and how this modeling for the mean source term is done, we will go look into this class of like the Eddy, Breakup, and Eddy, dissipation models. Okay. Now these are from Spaulding. Spaulding introduced the Eddy breakup model in 1971, and this is a very solid, I mean unlike the Eddy dissipation models, this is a very solid physical reasoning. Okay. So he said that the turbulent mixing can be viewed as a cascade process, and this mixing process is essentially is basically the most important factor that drives the reactions. We can assume that the reactions are so fast that the whole process of turbulent combustion to be essentially mixing controlled. So essentially the reaction rate in turbulent combustion, then we do not have to consider the individual reaction rates, whether in turbulent combustion the average reaction rate will be essentially governed by the average mixing rate. Okay. So that is the idea. So he says that the turbulent, that is the Eddy breakup model, says that the turbulent mean reaction rate is governed by the mixing, as mixing is the rate determining process. Okay. That is, the mixing time scales are much larger than the reaction time scales, which can be considered as a result in instantaneously or rather infinitely fast reactions, and essentially the whole process is governed by turbulent mixing. So the average reaction rate is essentially the mixing rate. So the turbulent mean reaction rate of products is given by is equal to rho times a CEBU, which is a constant, times epsilon by K times YP to the power of half. Okay. You see this thing, rather if you go back, what was the definition of our scalar dissipation rate? What was the modeling for our scalar dissipation rate? So this was the modeling for our scalar dissipation rate, right? As you see here, this thing looks very close to that. Okay. So, essentially the scalar dissipation rate has a unit of 1 per second, and here this is also when you this does not have any unit. So, essentially when it is epsilon by k, okay, this essentially gives you a time scale, because you see epsilon is as a time as the units of meter square per second cube, and k has a unit of meter square per second. So, epsilon by k itself has a unit of 1 per second. Okay. So, this gives you a time scale itself, and so they say Spalding is saying that this epsilon by k times yp fluctuation, that is the variance of y product fluctuation, variance of the yp prime is essentially this essentially gives you a mixing time times this dissipation rate by turbulent kinetic energy is essentially gives you a mixing time scale, and inverse of a mixing time scale, and that is essentially proportional to the mean formation of the mean is equal to the mean reaction rate of the mean consumption or mean production rate of the products. Okay. So, that is what he is saying. And of course, yp double prime, this one is the variance of yp double prime of essentially a variance of yp, whereas yp is given by mean yp plus yp double prime. So, this is not Favre average. Okay. So, you see what I was saying is that this epsilon by k times yp double prime square, okay, this whole thing is essentially kind of though this thing has a scalar dissipation rate, it's essentially the scalar dissipation rate of the products, and that is essentially proportional to 1 by time. But this is slightly different also, because scalar dissipation rate has a square here which is not here. Okay. So, this is what the Eddy breakup model is. Okay. It says that the essentially this the mean reaction or the mean production rate is essentially equal to the mean mixing of the mean mixing rate, and that is essentially inverse of the mean mixing time scale. Okay. So, that it is. Now, there is another model called the Eddy dissipation model. Okay. And this was done by Magnussen, and he replaced this yp double prime, they replaced this yp double prime whole square half with the mean mass fraction. Okay. That is in the mean yp, and they define these things if they consider that if they consider a reaction like a single step reaction plus yo going to yp double prime p. So, then this mean of for mean consumption rate of the fuel is essentially equal to mean rho times A is a modeling constant times yf times epsilon by k, and this mean consumption rate of O2 is essentially equal to mean the density times A times mean YO2 by nu times epsilon by k, and mean Wp is essentially equal to mean density times A times B by 1 plus nu, another modeling constant, and Yp times epsilon by k. Okay. So, this is the Eddy dissipation model, which actually now though it does not have much physical meaning, it actually includes this reactions through this one step reaction mechanism. Okay. So, this is the Eddy breakup and the Eddy dissipation models, and then there is one model which is the Eddy dissipation concept. Now, before that we can also use the detailed finite rate chemistry and write that as this reactions as a function of temperature, mean temperature. So, then of course, it does not introduce any models, but then the problem is that then you basically miss out the contribution that can come from the fluctuations of temperature. Okay. So, then that and as well as the scalar fluctuation. So, that is the downside. So, the Eddy dissipation concept is essentially Eddy dissipation concept is essentially this extension of the EDM, and is contains the detailed reaction. It can account for the detailed reaction kinetics though this is also crude and does not always have very solid physical arguments. So the assumption is that reactions happen in fine scales, okay, which is true to some extent. Reactions happen on small scales, and the small scale is essentially this we represent by star, which is a fine scale, and the reaction volume, the reaction length scale is given by zeta star. This is a constant. It is given by this nu kinematic viscosity times the Favre average dissipation rate divided by the Favre average turbulent kinetic energy squared to the power of 1/4 for dimensionality, and the the volume of the scales is given by, of course, this cube, okay. And the reaction rates, of course, are given by determined by the Arrhenius reactions, Arrhenius expressions. And the time scales, that is up to how much time the reaction will proceed, is given by tau star is equal to C tau, which is a model constant, nu by to the power of half, okay. So this is the time scale for the reaction, okay. And of course, to find out the boundary condition or the initial conditions for the reactions on small scales, the assumption is that pressure is equal to constant, and T and yi is of course defined in a given cell, in a computational cell. That is our initial T and yi, and the reaction time, that is how much time you will integrate up to these reactions, is given by tau star, and the integration is performed by some routines with ISAT, because this can lead to very stiff differential equations. And the model for the source term, which is the most important thing that goes into the governing equations, is given by this Si tilde squared time scale minus times yi tilde minus y tilde, okay. So it is a mass fraction. So this guy is essentially the mass fraction on small scales of species I after reaction time tau y star, okay. So by this model we can essentially go into we can put this inside our source term for this governing equation for the reactive scalars, whereas this thing can be always obtained by integration of the Arrhenius reaction rate, Arrhenius type reaction rate constants, etc., and by those detailed things, and we can integrate essentially up to tau star, as you said. So by this we can include the detailed chemistry into this source term in the models. But of course the physical reasoning is not very robust, and this is still a crude and first order model, and later classes we will see that how we can revise those models and what different techniques can be used for modeling turbulent combustion. So in this class we have essentially started looking into this what we have done is we essentially looked into the density varying flows and introduced a new concept called Favre averaging, and then with the Favre averaging we derived the different averaged continuity equation, we derived the average momentum equation. We showed what is that we can close those momentum equation using those momentum equation. When you do when you introduce Favre variables and you do an averaging, you basically encounter unclosed terms in the form of Reynolds stresses. We showed that how Reynolds stresses can be closed with essentially with the help of eddy viscosities, and which introduces this this Favre average turbulent kinetic energy and Favre average kinetic energy dissipation rate. And for that we can have a governing equation of turbulent kinetic energy, Favre average turbulent kinetic energy, and we can have a governing equation for turbulent dissipation rate. The turbulent kinetic energy governing equation can be obtained rigorously. The dissipation rate equation is basically kind of ad hoc, but with that we can model simple flows like jet flows, etc. Okay. Next we considered, because we are considering turbulent combustion, we considered basically this different kind of reactive scalars, where we put that species and temperature into one vector equation, and we wrote one general equation, and we saw that when we average that this the closure problem arises. So the closure problems similar to the equation for momentum, the closure problem arises in species, in averaging the species equations also. The biggest closure problem is of course the modeling the source terms, and here we have shown that the more source terms can be modeled using this Eddy breakup. The average source term can be, and of course before that we showed that the average source term for the temperature equation, which is the heat release rate equation, cannot be written just in terms of average temperature, because it also includes the contribution from temperature fluctuations. Okay, so that is the biggest problem of this kind of moment methods. And then here we show that if we just forget about that, we can use this Eddy breakup and Eddy dissipation and Eddy dissipation modeling and Eddy dissipation concepts to have kind of like ad hoc closure for this source terms. Of course the Eddy breakup model is physically sound in the sense that it says that the reactions are too fast, and as a result your average reaction rate in turbulence is essentially governed by the average mixing rate. Okay. So that is the argument, whereas of course one can use finite rate chemistry also, which is used in commercial softwares, but then you do not introduce any turbulence chemistry interaction, and you basically ignore the effect of this temperature fluctuations. So that is one penalty one has to pay. And then we looked into there are other problems also where the turbulent transport term closure also has a problem, and we showed that how for non-reactive closure, non-reactive species or non-reactive scalars, we can use a gradient transport assumption for that. That gradient transport assumption is justified, but even for a simple reaction where the reaction rate depends linearly on the species without even considering the exponential terms, Arrhenius terms, we showed that that can lead to a lot of problems in closures, and that does not hold under all circumstances. So here we have just started looking into turbulent combustion. We have looked into basically basic models and basic problems of turbulent combustion, the foremost being the closure of the source terms, okay, which arises due to the Arrhenius, once again due to the Arrhenius dependence of the reaction rate. The reaction rate is Arrheniously dependent on temperature, that is reaction rate is e to the power of minus Ea by RT. So that creates a problem, and that is the biggest one of the biggest challenges in modeling turbulent combustion. But then modeling must be required, because if you have to model engines where turbulent combustion happens in the combustor, you cannot use direct numerical simulations where we essentially solve from the large scales to the small scales. You have to solve for the average quantities, and when we saw that when we try to derive the governing equation for the average quantities, we face different kinds of closure problems, and which we try to circumvent in different forms. So next class we will look into turbulent non-premixed flames and turbulent premixed flames, and the modeling approaches for that. So till then, goodbye.